In this video, we will discover the conceptual framework behind logistic regression and SVMs. This will let you delve deeper into the inner workings of these models. This chapter is much more conceptual than the other chapters, because we'll be laying the foundation for understanding logistic regression and SVMs. We'll start off by exploring some math behind linear classifiers in this video. By really digging into the details, you'll be better equipped to compare these classifiers to other models and interpret the results. We'll start by defining a dot product. Let's create some NumPy arrays x and y. To take the dot product between them, we need to multiply them element wise. The result is 0, from 0 times 3, 4, from 1 times 4, and 10, from 2 times 5. The sum of these numbers, also known as the dot product, is 14. A convenient notation for this in recent Python versions is the @ symbol. X at y gives us the same result. In math notation, this is written x dot y. You can think of a dot product as multiplication in higher dimensions, since x and y are arrays of values. Using dot products, we can express how linear classifiers make predictions. First, we compute what we'll call the raw model output, which is the dot product of the coefficients and the features, plus an intercept. We'll then take the sign of this quantity. In other words, we'll check if it's positive or negative. This is a key equation in the course. Crucially, this pattern is the same for both logistic regression and linear SVMs. In scikit-learn terms, we can say logistic regression and linear SVM have different fit functions but the same predict function. The differences in fit relate to loss functions, which are coming later in this chapter. Let's see this equation in action with scikit-learn's breast cancer classification dataset. We create a logistic regression object, fit it to the data, and look at the predictions on examples 10 and 20, which are 0 and 1. Let's now dig deeper. We can get the learned coefficients and intercept with LR.coef and LR.intercept. Let's compute the raw model output for example 10. It's negative, that's why we predict the negative class, called 0 in this dataset. On the other hand, for example 20 the raw model output is positive, so we predict the other class, called 1 in this dataset. In general, this is what the predict function does for any x. It computes the raw model output, checks if it's positive or negative, and then returns a result based on the names of the classes in your dataset, in this case 0 and 1. Let's look at our prediction equation visually. This figure shows an example in 2 dimensions, with the raw model output labeled at a few locations. As we move away from the boundary on one side, the output becomes more and more negative. On the other side, it becomes more and more positive. So the sign, positive or negative, tells you what side of the decision boundary you're on, and thus your prediction. Along the decision boundary itself, the raw model output is 0. Furthermore, the values of the coefficients and intercept determine the boundary. For example, here I changed the intercept of the boundary. The raw model output at the same 3 points has changed because we changed the intercept. The boundary shifted down and left. To change the orientation of the boundary, we can change the coefficients. Here we're looking at different coefficients. This changes the orientation of the decision boundary. In fact, the 3 points we were looking at are now all along the boundary. In this video, we'll kick off our discussion of loss functions. Many machine learning algorithms involve minimizing a loss, and by understanding this perspective you'll be equipped with the tools to see connections between models, quickly grasp new ones, and start tailoring them to your data science problem. We have actually seen loss functions before, in the prerequisite course on supervised learning. For example, least squares linear regression, such as scikit-learn's linear regression class, minimizes the sum of squares of the errors made on your training set. Here, error is defined as the difference between the true target value and the predicted target value. You can think of minimizing the loss as jiggling around the coefficients, or parameters of the model until this error term, or loss function, is as small as possible. In other words, the loss function is a penalty score that tells us how well, or, to be precise, how poorly, the model is doing on the training data. We can think of the fit function as running code that minimizes the loss. Note that the score function provided by scikit-learn isn't necessarily the same thing as the loss function. The loss is used to fit the model on the data, and the score is used to see how well we're doing. It's intuitive that these would be the same, and they often are, but you should be aware that this isn't guaranteed. The squared error from linear regression is not appropriate for classification problems, because our y values are categories, not numbers. For classification, a natural quantity to think about is the number of errors we've made. Since we'd like to make this as small as possible, the number of errors might be a good loss function. We'll refer to this loss function as the 0 to 1 loss, because it's defined to be either 0, if your prediction is correct, or 1, if your prediction is wrong. By summing this function over all training examples, we get the number of mistakes we've made on the training set, since we add 1 to the total for each mistake. While the 0 to 1 loss is important for our conceptual journey, it turns out to be very hard to minimize it directly in practice, which is why logistic regression and SVMs don't use it. The reasons for this are beyond the scope of the course. Here, I'll minimize the function y equals x squared, which is computed using numpy.square. The second argument is our initial guess. Let's try 0. Finally, I have .x at the end to grab the input value that makes the function as small as possible. We got 0 as a result because this function is minimized when x equals 0. But that's not too interesting, since our initial guess was the correct answer. It's correct because something squared can only be 0 or more, thus, its smallest possible value is attained when x equals 0. Let's try another initial guess to see if it's actually doing something. What we see is a very small number, near 10 to the power of -8. This is normal for numerical optimization. We don't expect exactly the right answer, but something very close. This video, on loss function diagrams, is probably the most conceptually difficult video in the course. But when we're done, we'll see exactly what logistic regression and linear SVMs are, which will lead us, in future chapters, to understand why they behave differently. Hang in there. We want to draw loss functions, so let's set up a plot with loss on the vertical axis. On the horizontal axis we'll plot the raw model output. Since we predict using the sign of the raw model output, the plot is divided into two halves. In the left half we predict the one class, call it -1, and in the right half we predict the other class, call it +1. For concreteness, let's focus on a training example in class +1. Then, the right half represents correct predictions and the left half represents incorrect predictions. Let's now draw our 0 to 1 loss onto the picture. By the definition of the 0 to 1 loss, incorrect predictions, or mistakes, get a penalty of 1 and correct predictions get no penalty. It's important to distinguish this diagram from the decision boundary plots from earlier. Here, the axes aren't two features, but rather the raw model output and the loss, regardless of how many features we have. Also, keep in mind that this picture is the loss for a particular training example. To get the whole loss, we need to sum up the contribution from all examples. Using this type of diagram, we can draw the loss from least squares linear regression. As the name implies, this is a squared or quadratic function. In linear regression, the raw model output is the prediction. Intuitively, the loss is higher as the prediction is further away from the true target value, which we're assuming is 1 in this case. While this intuition makes sense for linear regression, it doesn't make sense for a linear classifier. For us, being really close to the true value doesn't matter, as long as we get the sign right. We can see this problem in the picture. The left arm of the curve is okay, the loss is large for wrong answers. But the right arm is problematic. If the raw model output is large and positive, the loss grows large even though we're correctly predicting +1. Since we're fitting a model by minimizing the loss, this means perfectly good models are considered bad by the loss. This is why we need specialized loss functions for classification, and can't just use the squared error from linear regression. Let's now look at the logistic loss used in logistic regression. This is the logistic loss. You can think of it as a smooth version of the 0 to 1 loss. It has the properties we want. As you move to the right, towards the zone of correct predictions, the loss goes down. We no longer have the interpretation as the number of mistakes, but, unlike the 0 to 1 loss, we can minimize this easily in practice. This is the hinge loss, used in SVMs. The general shape is the same as for the logistic loss. Both penalize incorrect predictions. These loss function diagrams capture the essence of logistic regression and SVMs. There are certainly a lot more details to come, but we've made a lot of progress, too. Thanks for watching. In the next video of the playlist, we will delve into the details of logistic regression. We'll learn all about regularization and how to interpret model output. Please feel free to ask any questions in the comments section. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. See you in the next video.